All musical instruments work the same way. You're setting up a standing wave, whether it's a standing wave in the string or it's a standing wave in the tube. But you are forming a standing wave. And the fundamental frequency, which is what you were kind of looking at last time with your straw oboes, is the lowest possible frequency for a particular tube or string. We also call that the first harmonic, which is why we labeled it in your little tables F1.
No.
Oh, that's good.
Zach.
Yes. Shh. Now the harmonics are those integer multiples. Remember we saw that we had those integer multiples, twice the fundamental, 3 times the fundamental, 4 times the fundamental, and so on. So we had those integer multiples. But this is how all instruments work. Just like my tube, I got resonance in it by forming that standing wave. The standing wave cannot form, you don't get a note. Which is why, like when you blow across a bottle, you have to blow a certain way to get that tone. Yes, you do. If you don't blow the right vibration, you're not going to set up the standing wave in the tube. Are you getting waves in the tube? Yes. Remember I showed you that little video of the liquid in the tube? Remember it got waves. When I went to the Exploratorium, and remember I got the one where it just kind of starts, just kind of went straight up. That's the standing wave. We got the standing wave in the tube. This is what's happening inside of the tube of your musical instrument. Anyone need a little more time? Anyone need a little more time?
Zach, you got it.
So, strings. Now, we're going to talk about strings and open tubes today, because our little discussion is going to be about open tubes, or the exercise. Tone tubes, depends on what it is, you know, just noisy exercise. Now strings. Now strings have a note at either end. First of all, you have to have a note at either end. Well, it makes sense for any type of string, whether it's on a string instrument or percussion, you know, guitar, a piano, a violin. You have to attach it at both ends. So you have a note at both ends. For the standing wave to set up, there has to be a note at the end. And the fundamental frequency has a wavelength of twice the length of the string, whatever that wavelength happens to be. Now, one thing to consider: what the frequency of a particular string is a little more complicated. It has to do with how long is the string, what is the tension on the string. In other words, how tight do you have it? Any of you have ever played a guitar or anything like that? No, if you tighten up the string, you loosen the string, it changes the pitch. Also, what the string is made out of. What is its diameter? What is its material qualities? Because when you look at a guitar, all the strings on the guitar are the same length. But are they all the same? No. I mean, when you buy a set of strings for a guitar, it's a 6-string guitar. You get 6 different strings. Each one has a different amount, different frequency, different thickness. You look at the piano, all the strings are different on that. Now, some are different lengths, and some are different thicknesses and things like that. On that sort of thing. So there's a little bit more complicated. We're just talking about one aspect of, so we're talking basically like one string on the guitar. This would be what would be happening on one string of that guitar, okay, on that. And that fundamental frequency has a wavelength twice the length of the string. We'll need a little more time. So we have some pictures to draw. So these are our strings. Now, I'm going to back up, so you see that. We're going to back up just a little bit. We talked about standing waves. When we draw a standing wave, that would be one wave, right? Crest and a trough. Even when we draw it in tubes, which are sound, a string, basically this is what you're getting. If you had an oscilloscope on the string, this is what you would see. This is what you would see on that. But in a tube, obviously, it's compressions and rarefactions, it's pressure waves. We'll still use the same thing to represent the standing wave. And when we do the standing wave, we go like that. Remember, isn't that kind of what it looked like with our little vibrating thing? You know, it had this, it's set, it looked like that. So this is what we call a vibrate. So one wave, this would be one wavelength. We have two antinodes. So remember, two antinodes make one wave. Two antinodes make one wave. And to show you in the string, let me show you quick. No. I actually took a picture of a thing that had a thing with a guitar. Just remembered that. See if I can find it. And I'm not going to be able to find it, of course. Oh, here it is. So I know it's outside, but this is a guitar. They kind of the strings, but we can see, and instead of a stroboscope, you roll this little plate that has little lines on it, so it's kind of a stroboscopic effect behind it. And notice each string has a different thickness, and when you strum them, notice each one has a different wave. Another one, yeah, that one is not very good as well. But you can see each one of these has a slightly different wavelength because they have different thicknesses and things like that. It looks kind of weird because the thing actually sits vertical, so the picture is sideways on that. But that's the kind of idea what we're going for here. Okay. All right. So when we draw this, okay. So fundamental frequency. Now the fundamental frequency is going to be, we want the largest wavelength we can have from node to node. So our first one, how much wave can I have in the first one? How many nodes would I have in the first one? One. We're going to start with one node. Or one antinode. We're going to start with one antinode because we have two nodes. One antinode. And that would be F1. F1 equals F1, the fundamental. Which means, how much of a wavelength is this? One antinode is how much of a wavelength? Half. That's half a wavelength. So the length of the string is 1/2 lambda. Lambda is twice the length of 2, which is what our definition is, right? Our last one we said that the wavelength of the fundamental frequency is twice the length of the string. That's the first one. We go up to F2, the second harmonic. Be twice F1. In order to get to the next antinode, we have to add more wave to this. To get to the next antinode, I have to add to get to the next time the node appears. So from here, the next time a node appears is one more antinode. So basically, we put a node in the middle, and we have two antinodes. Antinodes, something like that. So we've got from 1 to 2. Now the length is one wavelength. Lambda equals L. We go to the third harmonic. Now remember, the fundamental is also called the first harmonic. We go to the third harmonic. How many antinodes are going to be in the third harmonic? 3. Yeah, we go. So every time. So there's a rule. Every time we're going to go up one antinode. So now we have 1, 2, 3. 3 times the fundamental. The length is 3/2 lambda. Lambda is 2/3 the length of the thing. See if you guys can predict. Put in the next values. You guys on yours. Put in the, let's take out 30 seconds. You put in the next values. So, F4. How many times the fundamental is F4? 4 times. 4 times F1. How many antinodes are going to be in this one? There's going to be 4 antinodes. 2 waves. So 4 antinodes. 4 antinodes. Because we have 1, 2, 3, 4. So it's like if I went to the 10th harmonic. How many antinodes are going to be in the 10th harmonic? Be 10 antinodes. Yeah, 10 antinodes. How many waves are in this, though? How many wavelengths? There's 2, right? Because there are 2 antinodes make a wave, so there are actually 2 wavelengths. So this length of this is 2 lambda. Half L is our lambda. So there's kind of a progression here. You notice this? There's a progression. We start here. L is half a lambda. Then it's 2 over 2 lambda. 3 over 2 lambda, 4 over 2 lambda. So in other words, the length is going to be the harmonic number over 2 times the wavelength. You might want to write that down. This is a rule. The harmonic number, by the way, we usually designate the harmonic number as n. 4 over 2, 5 over 2, 6 over 2, whatever the harmonic number times the wavelength is the length. Notice here, we have 2 over 1, 2 over 2, 2 over 3, 4 over, 2 over 4, 2 over 5, 2 over 6. So for wavelength is always 2 over the harmonic number times the length of the 2. It's 2 over the harmonic number times the length of the 2. So that's just our rule. What's nice is the rules for strings are the same rules for 2 open ends of a tube. 2 open ends of a tube. Same rules. Picture looks a little different, but same rules. Anyone need more time? Now tubes. Now